Good morning, everyone, and welcome to E2E Network's webinar on improving the usefulness of LLMs and RAG by Kristin On, founder and head of customer success at Vespa.ai. I am Aishwarya, and I'll be your host for today. This webinar is brought to you by E2E Networks Limited, a mighty impaneled AI-first hyperscaler from India. Let me now take a moment to introduce you to our speaker of today, Mr. Kristin On. Kristin is dedicated to bridging the gap between innovative solutions and customer satisfaction at Vespa.ai. With extensive experience in all phases of software development and deployment, he excels in the operational aspects of large-scale systems, including architecture, sizing, benchmarking, and monitoring. His specialities include project management with global teams, computational linguistics, internet search relevance, and large-scale storage applications. Now on to the main event. Kristin, over to you now.
So thank you so much for the nice introduction, and thank you to the E2E team for inviting me. I'm really excited to be here today. So let me just take a moment to start sharing. See if this works. All right, let me know if you can see the start of the presentation now.
Yes, we can.
Okay, great, awesome. Yeah, so hey everybody, I'm Christian. I'm based in Norway. I'm here for you the next 45 minutes to go through RAG and how to make RAG applications great. I'll give you some hints and tips based on our own experiments and technology since last year. So let's just get started. So first, a little bit about myself. I've been in this space for 20 years plus, working on search and recommendation applications. I'm really passionate about creating and deploying applications at large scale and super obsessed about the quality. A little bit about what we are making in my team. It's the Vespa platform. It's been around for since 2017 as an open sourced platform with Apache 2.0 license. So you can download it and try it yourself on your laptop or run it in your data center. You can also use our SaaS endpoint if you want to use it as serverless. You have both options. The Vespa software is used by a lot of well-known companies, both small and large scale, for very different applications, ranging from media serving to retail, e-commerce, and also RAG applications. So we'll go through a few examples today. So my team is the Vespa AI team. We were in Yahoo for many years, working on a lot of the Yahoo services. Last year, we spun out with funding in October, starting our own company called Vespa AI. Its tech team is based in Trondheim, Norway, and we have people across the world in sales and marketing, helping teams all over to implement their applications, and we are still growing. So why are we here today? I think there is a lot of people asking themselves, there is so much going on in this space. What can I do to learn what I need to do? How can I use the new tools? Do I have to? So how should my stack look like? And like myself, I'm not a machine learning engineer. So how do I get started with this? And it's like every week there is a new model being launched or improvements to service. So the space is moving super fast. And I think sometimes it's okay to just go back to basics and learn like the fundamentals. And we'll do some of that in the talk today. There is a saying that it's like models come and go, things get constantly improved, but having a good overview of your system with good evaluations of your quality is maybe the most important thing. So keep that in mind too. It's a bit easy to be overwhelmed these days with all the news. So why is this important? So why are we talking about this? Why should we worry? As things go so fast, there are new concepts every day and people deploy new applications and we see new implementations. But sometimes the technology gets it wrong. So like Air Canada had a problem with their bot making false statements, and they were, made pay for that. So it's really, really important to have an eye on the quality of what we are implementing these days and the consequences of doing it wrong. So I'll go through first the agenda, jumping into the current state. We will talk about large language models. These are the models that are emitting the text that you see on OpenAI and similar services. We can learn how RAG can add data to the models to create, a good experience, and we need a good retrieval system to feed the large language model with the data. We'll talk about vector similarity that is used to extract the data for the RAG. RAG is retrieval augmented generation, by the way, if you didn't. So that means we have to get some data and feed that to the generative AI to, say, make a summarization. We'll also look at what you can do to cost optimize applications like this. When we are vectorizing our data, we create a lot of numbers. They will keep your memory growing, and of course the cost of the system's growing. That's good for cloud providers, but for your application, you need to pay attention to the size of your data and how to the techniques you can use to shrink the size of the data without lose precision or too much of the precision. We'll also take a look at how this fits in the bigger picture, other use of machine learning models, and as I said, going a little bit back to the fundamentals. So let's first go through some examples of what I mean when I talk about RAG. So perplexity.ai is a great example of a RAG application. So I suppose many of you have tried Perplexity before, but I'll go through a simple example. So whenever I'm traveling, I need a place to eat. Instead of using Google, you can go to Perplexity and just ask it to propose places. And in this particular situation, I was in Boston in the Back Bay area, so I just asked Perplexity where to go. And it presented this beautiful interface with, answers to my questions with, good suggestions. So I was looking into each one of them. So I'm not familiar with the restaurants in Boston. So when I checked this, I found that actually the first suggestion was an erroneous one. This particular restaurant was a 10-hour drive from my actual location. So something must have gone wrong here. So I also looked at, why was this suggested? And at the bottom of the page, we will see what the model also inferred from my question. I was hinting I was Norwegian, where I was, and those things. So to me, it seems like the system figured out that seafood was great for me. If you look at the sources on the top of the side, this is, by the way, a great way to illustrate RAG. This is what was retrieved as good sources for generating a summary. And the first source is the erroneous suggestion. That was a 10-hour drive from here. So this illustrates that, the service looks great. It's really compelling, but you have to be a bit skeptical about its content. So I was digging more into this. I was faking being an Italian, and I see that my preferences changed a lot, and that would also influence the summaries. Working a little bit more on this, just typing more questions, and I went back to the original question, and I get, for the exact same question, I get a totally different experience. So what happened here is that the model, after some of my questions, finally learned that I was making what we call a local query. It's like, I'm actually interested in restaurants close to where I'm at right now. So it presented the view with a map, and now it had great suggestions with restaurants very close to me. So this illustrates that the more the model learns about me, the better the predictions are, and the sources it used are also local kind sources. In this case, it's Yelp. So this is, I think, is a great illustration of how RAG systems work. The importance of selecting the best sources when you're making the input for the large language model to provide the suggestion. So I think services like this is the future. It's already here, and if you just step back and do the same thing at Google, it takes me back to the 90s experience. It's just a boring list of links. So it's definitely a good illustration of how important it is for services like Google to try to meet the competition from services like Perplexity. So and of course, Google is doing that. They have to be a bit slower because they can't really afford to make the mistakes that we can just see can happen, but they are investing a lot in it. So we will gradually see more changes to the interfaces inspired by services like Perplexity. So let's take a step back and look at the source of the data that goes into the RAGs. Most of the time it's very structured data. To the left here we see this copy of a document in green here, and we see it has different kind of fields like categories, titles. It has numeric fields like publish time. You will see an embedding here. That's an array of numbers. Use an array of authors, those kind of things. Very well modeled data. So to provide a good RAG, a retrieval system for this kind of data, you of course need text matching. One observation is when you do embeddings. Embeddings is a numerical representation of a piece of something, maybe a paragraph of text, or it could be an image. So it tries to be a representation. It doesn't necessarily mean meaning, but things that are similar, like similar text, will create similar embeddings. That's the way how to look at it. So the semantic search is built of vector similarity, but you also need text matching as things like names, locations, numbers, telephone numbers, those kind of things. They don't really work well with semantic search, so there is also always a text matching component in those systems. So text matching and semantic search together is often called hybrid search because it's a combination of multiple factors. Adding to that, you will also find use of machine learned models to do inference of your documents, adding to the ranking score. So you can deploy models like GPT models, or you can convert them to ONNX and deploy them into the system. Or you can just handwrite the ranking function. So finally, also an important observation: to create a good system, you need to add a lot of embeddings to the retrievable unit. In this case, it's a document. So that's called multi-vector support. In this case, we could have, say, the authors table here is an array of strings, so you could embed each one of them, or if it was an array of, say, reviews. So there is an unknown number of embeddings. So that means that your system must support arrays of embeddings too, and use the best one when scoring. So another example of a bit more complicated RAG system, it's Elicit. It's also a great service. I really encourage people to use that. So in this case, it's kind of not so one-dimensional as in the Perplexity case. In this case, I'm asking a complex research question. We still have the same RAG extracting, in this case, 8 results that are the basis for the summarization that is made on the top here. But you can also observe that this service also lets you add filters, and you can select things like publication year, a range, like a date range, study type, and these kind of things. So this also means that you also have to factor in things like filter and use these fields in the ranking. And as a later step, Elicit will invoke the models again to extract things like concepts from the data. So the RAG systems are fast growing, very useful and complex. It's a very interesting, I would say, time to be in, to learn as the engineers learn how to build increasingly more usable systems. So one of the most important underpinnings of RAG is the large language model. That's the thing that writes the summary for you at ChatGPT. So let's take a look at things that are of importance. So a large language model is what we call a generative model. It's like it creates things. It creates the summary that you see. So it's based on a foundation called transformer models. And they are good at predicting the next element in a sequence, and that's used for writing text. So we just saw the example of what they can do. Some people maybe call it autocomplete on steroids, and it's kind of true. It's kind of writes the next word really fast with really high precision. So to me, it actually looks like intelligence. Another concept that you probably have heard of is prompting. To make the model emit the data that we are looking for, like in one of the cases, like the restaurant recommendations, we need to provide some instructions to the model. So interestingly enough, that's just a piece of text written in natural language. I'm a developer myself. I find this kind of funny. I don't like it because it just, to me, it feels wrong to instruct something in natural language, not writing it in code. But that's the way it's done right now. But there are lots of things going on in the space. You can look at DSPy from Stanford, where it's a more programmatic approach to prompt the model or to instruct the model of how to formulate the answer. I'm not going to go into details into prompting. There is a lot of stuff you can find on the internet on how to write good prompts. I think that is something that will not survive long term, but it's the way to do it right now. One problem with the large language models is that it takes really a long time to train such a model. So this is from February. That was GPT 3.5. So that model, it actually said that I was, last updated almost a year before. So I don't have the knowledge about the King of England. At the point of model training, it was a Queen of England. So that means that the model itself has factual information, actually a lot of it, but it might be stale. I did this query again some months later this year. This was in May. So we see the latest update was, a year later. So the model had at that point in time learned that there was a King of England. But still, we can see that the model is, lagging. The model has a lot of things that it maybe should not have. It's trained on public data, depending on what kind of model we are looking at. But the ones that you're using at OpenAI, like ChatGPT, it's trained on the data you find on the internet. And that could be data that shouldn't be there. Like in this case, we are trying to find out how to break into systems. And the models can be very assertive and write good text that make absolutely no sense. This is an experiment I just did with the Mistral 7B. I was just querying for, it looks like the same local query I made with Perplexity. And of the 5 restaurants it suggested in Berlin, none of them exist. Actually, well, the last one, the Grand Colbert, exists, but it's in Paris. So the output here is just totally wrong. It's as expected, as this is a much smaller model, so it doesn't know that much, but still, But looking at the text, you really believe that the model knows what it's talking about, but in this case, it doesn't. That's called hallucinations. All right, moving on about RAG. So this is the architecture of RAG. This is how it's built. So on the left side, you see a user making a query. That query goes into the content through a search. So that's the retrieval part. That's the factual data you want to feed the model with. That could be your product database, or it could be your inventory of media articles, or whatnot. So that provides a result, say 10 results, that is added to the prompt and sent to the large language model. So in this illustration, we say large language model client because it's really an interface into, say, OpenAI, or it could be use of a local model like I just did with the Mistral. So that will write the responses back. As the LLMs are quite slow, so we can't wait for the full answer. So that's why you see the stream of tokens coming back. So that's also a treat, you will see from the LLMs that that's how they work. They kind of give you small nuggets of information as you go, so you don't get impatient. So at the end, you will see the result. That's the basics of a architecture. So going back again to the original example, we will focus here on the sources. So this is what was retrieved from the database at the right of the illustration here. Okay, so I made some experiments first. So first I made this small little database to myself just by synthesizing some data, doing a text search on my 10 synthesized records about the French restaurant in Berlin. So this is what it takes to for a RAG system. It's the user query. It's added to the prompt with some instructions to the model. For the Vespa implementation of RAG that I'm using here, I'm specifying a search chain that involves calling the local the model I'm using, and the query itself, where I'm just selecting from the restaurant's database. So we'll see that it extracts 2 hits. In this case, you will see in the middle of the screen, and it extracts the wrong things. The first hit, it says taxi in Paris, which definitely is wrong. And the other one is another restaurant that's also in Paris. So doing a regular text search didn't work well for this particular case. So we have to do better than that. So let's talk a little bit about vectors and embeddings. So at the left hand of the illustration, you will see hello world. That's the textual part, like in a query. So what happens is that is tokenized into the numeric space. So it's just a list of tokens that goes into what we call the embedding layer, or into a model that would generate embeddings. So in this case, it's just generating a vector per word. It could be a vector per paragraph or a vector per something. But at the end, you will see embeddings. You can embed other things too. You can input things like images or audio or movies. Again, out at the right-hand side, you will just see a list of vectors. So things that are similar, like similar text, will create vectors that are similar, that has numbers that when you compute the distance in vector space, they will be close to each other. One common used distance metrics is cosine similarity. There are others too. So for binary vectors, you can use Hamming distance, and you can also use angular distance. And those, I think Vespa supports about 6 or 7 of those. So you will use the distance function that is most suitable for the model you're using. So we're going back to the same query again. I'm making the experiment. I'm querying for French restaurants in Berlin, and this time I'm using a nearest neighbor search over my embeddings. That's the bold text in this case. So extracted from my database then is two different restaurants. We don't see the taxi example here. We see a restaurant, the Berliner Bastille, which looks right. It's a French restaurant in Berlin. And also the second one is still wrong because it's in Paris, but it's like it's better. So using embedding means that it's in this case selected restaurants and not taxi companies. So that's why semantic search is able to do more like fuzzy kind searches, and it will always give you results because there is no concept of no hits when you're using vector similarity. Every vector is a candidate in the response, but the distance from the query vector is the ranking criteria. So let's go back to what makes this system still not functioning. So if you remember the slide about structured data, most of your data in your applications where you work or where you're studying, you will see it's structured like this. It could be records with names and addresses, and in this case I just added city. So if I just filter on the city field, I will expect to have only restaurants that have city equals Berlin. So let's try that, and I add this filter, and then I get 2 restaurants from the correct city. So filtering is also very important in RAG applications. You have to provide filters like geo filters, or it could be time filters like that. So this is definitely a step in the right direction. So that means that vector similarity alone will just give you some results, but not necessarily the right ones. So meaning to the left of the illustration I added, but there is much more data we need to feed to the system. It's the concept of me being at a location, and we need to feed that in the query formulation when we are extracting the data. Right, so how do you do this? So in most search systems like Vespa, you will have some definition of how to rank your results. To the left, we see the semantic rank profile. We see the input, which is the query embedding, meaning the numerical representation of what I was typing, and an expression that just ranks on the closeness between the query embedding and each document's embedding. So that had the problem of not capturing the location exactly. Whereas a more complex application, you will do a hybrid where you have a combination of the semantic using a closeness, but also text signals like BM25, matching of your fields. BM25 is a well-known function to generate scores based on how well the text matching is. And in this case, I'm searching for Berlin. So we will expect that things with Berlin in it will have a good score. So making this even more complex, it will look like this. We will have in the query, we will see a nearest neighbor operator with the embeddings, and we will have an OR term with the user query for the text matching, and we will have the filtering on location, and you can have more filters as well. Say I'm only interested in restaurants with very strong ratings. So with this, we will see that just changing the ranking profile from the pure semantic to the hybrid case, we will see that the restaurants will rank differently, which is expected. Like in the case on the right-hand side, we will the impact of also adding text ranking will make the Belmondo French rank higher. So I won't go into details why that is, but the takeaway is that you need to add a lot of signals into your ranking functions to create good results. So one thing you need to consider is that this is how you kind of this is input to the language model, and as with internet search, you will also see that the spammers also know this. So we will see a lot of developments in the way that people create text that is available for the internet that is actually targeted for language models in attempts to rank higher. All right, so moving on to something completely different, we'll look more into vectors. One observation is that when you are embedding your data, you create long lists or like vectors of numbers, and a number can be take a lot of space in memory, or not so much. So one way to create embeddings is, of course, to just call services like OpenAI. So the pricing is quite low. So unless you have a lot of data, just do that. But in this talk, I'm also going to talk about use of local models, and that is for cases where you can't send your data to OpenAI because of policies or regulatory restrictions. So for those cases, you need to consider the cost of generating and storing vectors also. So let's look at the size of the data that you're generating. Very few models use doubles as value types in the vectors. You will see floats and B floats quite often. Still, they take like 4 bytes or 2 bytes. But the developments recently are like doing quantization. You will see smaller and smaller data types that will go to 8-bit or even 1-bit. So that has a great effect on the memory requirements for your system, but of course you lose a lot of precision when you are shrinking your cell value type. Another thing to consider is dimensionality. Like the more numbers you have, the more precise your vector is. So this is a moderately sized vector. So one observation is that when you are embedding textual data or any data, not all of the columns are equally important. In a vector like this, you will see that like the red ones might have the best the highest rate of information, meaning the highest variance. Some of the indices into these vectors will have little variance, so you can cut them and lose little precision. So traditionally, teams used PCA as a way to identify the most important vectors, so you could discard the less important ones. Recently, we had, I think this was in March this year, the concept of Matryoshka embeddings. Matryoshka is a way to train. So the output vectors are sorted in importance order. So you will see the first indices in the vectors have the most information. So that means we can cut vector from the back and lose little information. So the precision will be almost unchanged, but you will reduce the requirements for your memory. So this is a really great way to optimize for cost to make your application viable, even though you have lots of vectors. So these are to the right. It's an experiment we made in our own system. We just started with a vector with one dimension and measured the quality of the results. And you will see the green graph. It will like the quality increases with number of dimensions when you get to about 100, where adding more dimensions doesn't really add more to the precision. So that means that if you go from 100 to 200, you double the cost, but you don't really get better precision. So this is a great way to cut the data size in your application by just using the Matryoshka embeddings. So to the left, we see the measured standard deviation for the vectors starting from the most important ones to the least important ones. So this is a good illustration that we can start from the right and cut vectors until we have, the right precision level. So this is the cost precision trade-off. So why are we working on this? So the goal of this is to move data from memory to disk. This is, I think, from an AWS pricing page. So we'll see that if you are, putting data on disk, you can put so much more data per dollar on disks than in memory. So moving out of memory to disk will have, great effects. So to do this, you can't just shrink both the cell type and the number of dimensions because you will lose precision. So how do you address that problem? So we'll take one step back and look at what's called multi-tiered ranking. I think the best example of this is you do a search on Google. So how does Google respond within 100, 200 milliseconds? So what happens is that the first phase ranking in Google is running a really cheap ranking function to discard most of the candidates really quickly. So you're left with a smaller candidate set, and then you can increasingly use CPU to modify and re-rank the surviving candidates. So this will happen in multiple phases. This also means that for this particular scenario, we can use in the early ranking phase, we can use low precision vectors to discard most of the candidates with just, very little memory usage. So in this case, I call this binarized query embeddings in this case. So those binarized embeddings we can put in memory compared to, say, a bfloat. A bit is 1/16, so that in these cases, in the RAG cases, most of the time your cost is driven by the memory requirements, not the CPU. So we will shrink the active memory by just putting binary vectors into memory, and we'll put the full precision vectors on disk instead. You will see at the bottom here. In this case, it's a float. So that makes it 32 times larger. So for this particular multi-tier ranking case, we will see that we were able to shrink the data to 3% of the original, just by doing quantization. And if you also shrink it with the matryoshka and you reduce the number of dimensions in the vector from the least important ones, you can shrink it maybe to half or even better. So this is a well-known technique to use multi-phase ranking and different kind of precisions on your vectors to optimize for cost, but still keep the same precision. I'll just skip over this, but it's just even more complex multi-phase rankings. Yeah, let's look at HNSW indexing. Some of you noticed the use of what we call an approximate nearest neighbor query operator. When we are looking at vector distances, you can always do an exact computation, but that doesn't scale with a lot of elements in or a lot of embeddings. So we have to do approximations to make this fast. And one of these most used libraries is HNSW, which essentially is a graph where you have multiple layers, where you start on the top and you navigate increasingly denser neighbors, but you are making a graph traversal, so it's really quick to eliminate most of the space. So that means that when you're inserting a node into an HNSW index, you will have to evaluate, given my point in space, which are my neighbors. So an insert into the index is also a search. So you will find that feeding to those systems can be a bit heavier on the system than without the index. So the things you need to consider is how many neighbors to explore when you're inserting and how many links you are making. Another thing important for good RAG applications is that you need to update it as you go, so the user experience is based on real-time data. So the Vespa implementation of HNSW is also built for being able to update or remove items from the graph. Another thing to consider when you're building RAG applications is that you will grow with data or you will grow with queries. So you will have to be able to add capacity or remove capacity from the system or reindex the data in it without taking it down. So you will have to look for technologies that is able to dynamically adapt to different sizes of your clusters. So to get started, I said that we want sometimes to just go back to the basic, and a thing you can do is to get your hands dirty by just trying this yourself, building a simple RAG system. I know the E2E team will distribute a copy of this presentation after, so you don't have to write this down. But the components you need is a query engine like Vespa or others that you feed the data to in one container, and you need either to access an LLM through an API endpoint or run your own model locally. You can use Olama for this. It's a great tool. So in this particular example, I spin up 2 containers and I connect them on the same network. And I have built a RAG system using the architecture that you saw earlier. So it's as easy as this if you want to try it out, and you are always very welcome to contact me also as well if you have questions about this. So in summary, we did an intro into how RAG applications look like, looking at Perplexity, a very popular application. We looked at large language models and how they are limited in their abilities and things to look for. So we looked at the RAG architecture and how important it is to build a good retrieval system. I used a very basic example. This gets very more complex, but we are very concerned about the retrieval part because it doesn't get any better than the data you're feeding into the model. We looked at how to optimize for cost by reducing the size of your data, of your vectors used in the semantic similarity by just shrinking the cell values and have less dimensions. And finally, we also looked at some of the important things to consider when you are indexing and how to measure performance. I also include for your perusal after this presentation some of my best suggestions for follow-up reads. You can learn about how to build systems like this. Mixspread is a great read on neural search, and of course Hugging Face and what goes into quantizations in much more details. So also call to action. I think that in the future we are going to build systems like this by thinking in vectors or actually in more dimensions with tensors. So you will formulate this is an example from a retailer where you're having large-scale matrices with product matrices with products and all its attributes and how they interact with the users and how you're using this in to generate a set of recommendations. This is a really good blog post on how the future recommender systems will be built. So it's a good read. Right, this is also an analysis from Apotanskanen. It's a good recommendation of a comparison of the technology. I think it's a month old, so it's still valid. Definitely worth a read. I'll skip this one. All the language models are based on the Transformers, a 2017 paper from Google. Read this to understand a lot of the underpinnings. moving fast here. I recommend using the Vespa blog, blog Vespa AI, to learn more about these concepts. These are more like generic blogs on things I just walked through on how to optimize for cost, how to measure precision, and build strong retrieval systems. There is also a newsletter you can subscribe on, and some pointers to who to follow on Twitter and LinkedIn. Okay, I think that's it. I'll hand it over to the E2E team for Q&A. Thank you very much.
Thank you to you, Christian, for this insightful session, and a big round of applause for all of you who joined us today and participated so actively. We can now take up a few questions. You can write your questions in the chat box. We'll take up.
Yeah, so I don't have the questions in front of me, so please, read them in your favorite order.
Okay, so before you all leave, we are eager to hear your feedback on today's session. Please take a moment to fill out our quick survey. Your responses are incredibly valuable and will keep us improved to our future webinars. I'll quickly run the poll. While you all fill the poll, let me give you a quick introduction to what we do at E2E Networks. E2E Networks Limited is the leading AI-first hyperscaler from India, focusing on providing advanced cloud GPU infrastructure. We lead the industry as a prominent cloud GPU provider, offering a comprehensive range of NVIDIA GPUs, including Edge GX H100, A100, L40S, L4, A40, P100, and T4s. To know more about us, you can check out our website, e2enetworks.com, or if you want to get your hands on any of our GPUs, you can sign up at my account, e2enetworks.com. I'll be posting the link to both in the chat box for your reference. Thank you, everyone. That's all from us today at E2E Networks Limited. We hope you found this webinar valuable. Stay tuned for more such events from E2E Networks. Have a wonderful day ahead.